All right, I have a copy of the key posted in Moodle, I think. Here it is. I know that writing comes in a little bit light, so the first one, you just take the angles of the three axes with the vector. So cos 1600 magnitude times cosine 67 times cosine 32 and times cosine 111 should get 625, 1357, and minus 573. The units on that is newtons. So that was one thing I didn't really mark on that, this. But I will in the future more aggressively, or more, I don't know what the right word is, more diligently. I should have been newtons on that. Okay, so get your units in these things when you're doing these. Okay, the next one there, what do we got? We've got a force. Now, the first thing we got to do is we got to get it down into the XY plane. So to do that, we go cosine 35, and that applies to the X and Y axes, okay? Then we've got to get it onto the different axes. So this angle here is 117, so that'll be cosine 117. That's the I component, or the I unit vector, maybe I should say, unit vector component. And then we've got cosine 27 for the y-axis. That's shown right there. So cosine 35 gets us down into the plane, and then cosine 117 to the x-axis, cosine 27 to the y, and then we got 55 left over. That's 90 minus 35 gets us 55, so that'll be cosine 55. And then we multiply all that by 3400. And you get negative 1264, 2482, and 1950. Okay. So that's a double projection there. Okay, the last one's just a position vector. So you want RB, and that's 1.4, 0, and 1.6, and then you take away RA, and that's going to be the negative of 0.9, 2.1, and negative 0.6. So what you get there for the position vector from A to B is 0.5, negative 2.1, and 2.2, okay? Like so. So that's the first page there. So we got any questions on that? Okay. Okay, the next page there, what you've got for this first vector, or actually vector C, is 1.5, that's the x, 2.1 is the y, and negative 0.6 is the z, okay? And then what you got up here for C is for D is 1.2, negative 0.7, and 2.4. And so what you do then when you want that vector is you subtract them. So RD we've got, and that's 1.2, negative 0.7, and 2.4. And then you subtract RC from that, and you get 1.5, 2.1, and negative 0.6. Do the subtraction, and you get the vector that goes from C to D, and that's negative 0.3, negative 2.8, and 3.0, okay? Then what you do is you do the theorem of Pythagoras, and you'll find the length of RCD, and that's 4.11. Then you divide through by that to get the unit vector. So this will get you UCD, and that's 1 over 4.11, negative 0.3, negative 2.8, 3.0, and that'll get you the unit vector. And then to get the force vector, what you do is you take the magnitude of 4200, that's the force magnitude, times the unit vector, which is 0.0729, negative 0.681, and 0.729, and that'll get you the force vector. Okay, and that comes out to be negative 306, negative 2858, and 3062. Units on that are newtons. Okay, so that's how you find the force vector. Good with that? Okay. Had a number of little mathematical errors on that, but most everybody did a good job where I could just say, okay, you know, dropped a negative, did this, did that, take a point off and get them down the road, you know, that's fine. So that worked out fine. You know, people did a good job of tracking their work for the most part. Okay, the next one, this is a dot product. So what you want to do is find FEF. Now, you know, we kind of talked about this yesterday. On that back page, I gave you the unit vector for EF. So that's 0.432, negative 0.384, and 0.816. So you just factor that up by 7,000 and you get FEF. So that's 3024, negative 2688, and 5712. So that's the force vector FEF. And that's newtons. Okay, then you need the unit vector for the line you're projecting onto. Now that's EG, so the unit vector for that is 0.696, negative 0.642, and negative 0.321. Okay. So to get the projection there, you just dot them is what you do. So when you dot vectors, you take the like components and you just multiply them together. So that's 0.696, that's negative 2688 for the y, and that's times negative 0.642, and then you've got the k, and that's 5712 times negative 0.321. And do all that, and you get about 1997 newtons. Okay, so that's the compressive force. All right, now if you want the compressive, now the important thing on that is you add those products together. 2105 plus 1726 minus 1834. Those are not XYZ components. Those are things that you add up. You add up the products and get the total, and it's 1997. Okay. So if you want to find the compressive vector, you take that 1997 and you multiply it by the line that it acts on, the unit vector for that line, I should say. So that's 0.696, negative 0.642, and negative 0.321. That's the unit vector from E to G. And when you do that, you'll get the compressive vector now. 1390 minus 1282 minus 641. Okay. All right, and there we go. So there's the compressive vector. So you got questions on that? Okay, we're good. All right. Now we're using the same setup here to find the moment about G. All right, now the important thing here is you are going from G to E. So what you want to do is take RGE. Okay, and that's minus 1.3, 1.2, and 0.6. And then you cross that. So first thing that goes in there is that position vector. Now notice that goes from G to E, not the other way around. Okay, so from G to E. And then, and that is also a position vector. It's not a unit vector. Okay. So we want the position vector, and then you just want to cross that with the force vector, which you used on the last problem, so you got it right there. And then we got I, J, K. Okay. Just do a cross, and you'll come up with the moment vector. And what is that? 8467I. Plus 9240J minus 135K. So the important things on that cross is it's got to be a position vector from G to E, not a unit vector, but a position vector, and also G to E, not E to G, but G to E. And then you cross that with the force vector. So the position vector first, the force vector second, okay? And then if you want the magnitude, you take the square root of sum of the squares, 12, 5, 3, 3. Everyone okay with that? Okay. Okay, the next one, you take your moment vector from the previous page. Now you might have had, you know, a bust on that. If so, I just looked and saw what you had for your moment vector. And then you dot that with UGH, okay? So that's 0.987, 0.135, and negative 0.09, I think. Just dot them together. So just multiply the like components together. And then just find the products and add them up. You get about 9,592. Newton meters are the units on that. Okay, so what's your units? So that's just a dot. Okay. Questions on that? Good to go with that one. Okay, the next one's an equilibrium problem. What you want to do there is get the forces in columns. So OJ, what it does is go in the negative y direction. You're told that in this little statement down here, okay? And it's, if you look at the sketch, it's parallel to the y-axis. It's on the negative y-axis. So that's 0, negative FOJ 0. Now, OK, what that does is right here, that's FOK times 0, because it has no x component, minus cosine 51 in the y, cosine 39 in the k. All right. So see what that thing's doing is it's making a 39-degree angle with the positive z direction. It's shown that it's in the x or y z plane. So 39 is the angle with the z-axis. 90 minus 39 gets you 51. So that's the angle with the negative y-axis. Okay. So that gets you negative 0.629 FOK and plus 0.777 FOK. Okay, and then a 0 at the top. Okay. And then we got FOL. So that's in the negative x direction, so that's negative FOL 0 and 0. And then we got F1, which you found on page 1, so that's 625, 1357, and negative 573. And each of those rows then are for the x, y, and z directions, so they add up to the 0. And then you just solve. And it, it's a pretty quick solution. X gets you 625 for OL. Z will get you, it's a K, so that's 738 for OK, and then you plug that in on the Y equation, you can get FOJ, it's 893. Okay. So just get those forces in columns, solve out the rows. Okay. All right. Any questions on that one? Might have been a couple different ways to solve this last one, but we're working with EG, so we want that unit vector, 0.696, negative 0.642, 0.321. Well, what that does, that points in the direction. If you want the vector from E to M, you take that unit vector and multiply it by 3, and that will get you 2.09, negative 1.93, and negative 0.96, basically. So that's the vector from E to M. So you just take the vector at E, which is 0.6, 1.2, and negative 0.5, and you add this vector to it. So that's 2.09 minus 1.93, and whatever that last one is there, negative 0.96. Just add everything together, and you'll get the position of M. 2.69, negative 0.73, and negative 1.46. Okay. So that's the last one there. All right. Okay, so that's basically the deal with that one with the key. I posted the key in Moodle. Okay. Now I felt that was a little bit long, you know. So what I did, I curved it a little bit. So the numbers added up to the number on your front page that I crossed out. But then what I did, I kind of looked at it, and I curve in a maybe somewhat of an odd way. I take the points you got off. So points off, points subtracted, you might say. And then I gave you 20% of them back, okay? So that's how I curve. So it's your score plus 0.2 times the points off, okay? And that was your final score. So if you got a raw score of 80, I'd take 80 plus 0.2 times the points off you got, which would be 20. So that would end up equaling an 84. Okay. So we okay with that? Average was about 78. Now, after I curved it, it was about 78. Okay. Yeah, I'm sorry about that. That was a little long. You know, I kind of realized that after the fact, but so that's, you know, I did that to compensate back for the fact it was long. Now I would comment though, you know, be thinking about next year. I mean, next year at OSU, it's a different environment, okay, and you got to kind of get used to that. Probably the best class you have to prepare you for that environment is physics. It's, you know, they just keep throwing stuff at you, and you know, you're supposed to pick it up, and you get tests where they're always too long, and you just got to do the best you can on them. So just start learning those skills at dealing with this, you know, whatever those might be for you. But you know, I tried to make that clear about that last page, but that definitely cost a number of you some time reworking all those vectors. So, you know, be aware of that. The other thing is, you know, on this one, I told you there will be moments, there will be dot products, you know, there will be finding forces from position vectors. You know, I flat out told you that. And so, you know, to really prepare for this thing, you should have had that drilled. You should have known to do a moment, I take a position vector with a force vector and I cross them. And, you know, I mean, you know, especially, I point that out about the moment problem because there seem to be a lot of people having some problems with that, you know, using the wrong type position vector generally. And, you know, you can't afford to be scratching your head about this stuff. You just don't have the time on test to do that. And the other thing is, you know, I should have had that pretty well wired down, I mean, frankly, to really do well in this test, and just got the position vector, got the force vector, done the cross, moved on with it, you know. That's kind of the approach you want to be taking on these things. It's just the environment you're moving into too at OSU. I mean, you'll find that out next year. Okay. All right. So we got any questions on that? All right. Okay.
What week are we expecting the second test?
Second test is either late week 7 or early week 8. And this will be kind of the drill for all the classes, you know, that you take from me. There's a couple midterms. I'll get you a review beforehand that has some old problems off of old tests, just so you got some idea what they look like. That's pretty typical of how I'll, you know, get you a review and all that. Okay. Okay. There you go. All right, why don't we have a look at the homework then? Okay, the first bit here is the free body diagram problems. Now you can just take these sketches and turn them into free body diagrams is probably what I'd do. Again, if nothing else, just on a test. I mean, you're gonna get some of these things to do on a test probably, for sure. And, you don't have time to be digging out a straight edge and making a free body diagram all over again. I just take what you got, turn it into one, okay? Now, the whole thing on this free body diagram process is, usually they tell you don't have tunnel vision, but I think on this you do want to have tunnel vision, okay? So I look at a smooth surface there. I see a flat surface that rests on it. I know the reaction is perpendicular to the flat surface. That would be RB. I'm drawing a free body diagram of the porch, okay? That's the underlying thing. So, here's what I'm drawing the free body diagram of. Okay, I see that cable, okay? Cables, the force acts along the line of the cable, and a cable pulls. Now, I do want you to find and dimension the angles, because that's very important there. So to do that, I take an arctan of 1/3 and get that angle. And then I would just go ahead and put that on there. So as part of these problems, I want the angles dimensioned right on them, okay? Because you need that to solve the problem. So you want to get used to putting that on your free body diagram. So I don't know, it's 20-some degrees, I think. 18 degrees. Whatever that comes out to be. 18.4 degrees. Okay. All right, and then we've got a cantilever fixed support. So that has an RAY, an RAX, and a reactive moment. And then we got this wind force over here. So there you go, there's the free body diagram for that. So that's 18.4 degrees. Yeah, question there.
Isn't the force of wind pressure?
Yeah, the force of wind is a pressure, right? It's distributed over the side of the porch. It looks like that's probably been what I call resolved into a point load. So the pressure has been multiplied by the area already, and we have an assumption of a wind force. So someone's done a step already on this one. Okay. Other questions? Okay. All right. Okay, the next one there, again, just get your tunnel vision goggles on here when you do these. You see a pin joint. Pin joint has two reactions in the X and Y directions, right? No moment reaction though. So that's a pin joint right there. This is a roller. Okay, so the roller reaction is perpendicular to the flat surface. That's the general rule when you've got rollers and such. Okay. So get that reaction at B in there like that. Be sure that you dimension this angle right here. So figure out what that angle would be. Okay. All right with that?
forces with each vector?
Well, to drop the forces, just show them as arrows, I guess. And show if they do that, if they're not horizontal or vertical, show the angle that they lie at.
Okay,
You know.
but in terms of.
Oh, yeah, you don't know. I mean, you're not going to solve for the magnitudes on these because they're unknowns. So just label them as reactions. Now, of course, this one, that one's whatever, 190, is it? 190, that one's given. But if they're not given, just list them as, some sort of unknown. Okay, with that. Okay, then we got this one here. Now this one is all about, this one's put in here purposely, smooth. So we got surfaces are smooth. Okay, so that means the forces are perpendicular to the flat surfaces. Okay, so you have to identify for each one of those four reactions what the surface is, and then what direction the reactions are pointed in. Okay, so if they're not vertical or horizontal, label the angle that they lie at. You are given the fact that this big glass plate is at a 67-degree angle with the horizontal there. Okay. Any questions on that? But that's kind of an exercise in just understanding how those smooth surfaces act and to get those angles in there properly as you need to. All right, good with that? I want to go away. Okay, so this is an exercise in what causes forces, okay? So you're drawing a free body diagram of the pipe at A. Now certainly you have a weight acting on that. So that would be the weight at A, and that's kind of part of what drives all the reactions. Now what causes reactions is contact here. So what you want to do is look for points where there's physical contact, and that's where the reactions are. Because the two things that cause forces are body forces, which are for us, this is gravity, which leads to weight, and then the other thing is physical contact. There has to be contact to get forces. Yeah, question?
We have a slightly different diagram than you have displayed. Does that really change our answers?
What do you got? Do you got like a big stack of pipes with walls on the side?
Yeah.
Yeah, okay. Yeah, it doesn't make any difference really, because you're still going to have those 6 surrounding pipes. I think I just did that. I don't even know why I did that, but I did that. Yeah. Okay, so yeah, it'll lead to the same one for pipe A, so we're good. Thanks. Okay. So, and then figure out the directions of the forces and then label them, okay? So if you've got a force on there, that's going to be a reaction, whatever you want to call it, but get the angle in there, whatever that angle happens to be, okay? And remember that forces are normal to the flat surface, and also if you've got tangency here, use the tangent line as your flat surface, okay? So use, on those curved surfaces, use a tangent line and consider that to be the flat surface. You all good with what I'm saying there? Okay. Good with that? Okay, we've got a couple there. We've got a pin joint. That's what that, triangle is a pin joint. And then we've got a roller there, okay? So, and then you've got a couple there, all right? And you're given the magnitude of it, so, include that on the motor, okay? So we want a free body diagram of the plate. So go ahead and include that couple, remember that, because that's being applied by the motor. Plus you got a pin joint and a roller, okay? So, try and get these things drawn, in a good way so you can solve the problem. If you got a good free body diagram, the problem solution just kind of falls out usually from there. So get in the habit of getting a good clean free body diagram drawn. Okay. We okay with that? Okay. Then we got a couple equilibrium problems. Just remember to start off with good, clean, free body diagrams on this. This one's very similar to what we did in class. So, you got a pin joint there, plus you got a cable force there. Sometimes they use T for tension on those for some reason. So you want to solve for those forces there, come up with a good strategy to work through that. Okay. And solve for the three reactions. I can't remember, are there answers on that one? The book?
Let's see.
Okay, why don't I give you answers for those just so you know what you're shooting for. If I can find the stupid thing. I've got, so RAX, RAY, and tension B and tension BC. What I've got is 16, 17, 4200, and 3, 2, 3, 3. And they're all newtons. All right, so that's one of them to do. We got any questions on that one? Okay. The other one's a little bit more involved, perhaps. What we got there, I don't know, it's not too bad there. We've got a distributed load triangle and a rectangle. And then we've got a cable there with it's being tightened up. And then we've got the fixed support at the cantilever. All right. So what you're going to want to end up doing here is coming up with a free body diagram of this. So you're going to have to cut the thing up into a triangle and a rectangle. Okay, that's how you handle these trapezoids. And then you're going to put the forces associated with each at the centroid of the load. Okay. Like so. There we go. All right, now you've got a cantilever over here, so you've got three reactions associated with that. So your actual approach to working through this is not really complicated. It doesn't involve a strategy on what I should do first and second and that sort of thing as far as working through the equations. What you're going to do is you're just going to apply the three equations there right at the support, okay? Well, the force equations are applied anywhere you like, they're just directions. But the moment would be applied at the support is usually what I do. Okay, we also have that cable force pulling up into the left, like so. And I think that's 3,000 newtons if I remember right. Now we got 62 up here, that's with the vertical though, so watch that. Normally we work with angles with the horizontal. Now you don't have to, but we're often just very used to that. Often people think cosine X, sine Y, but that's if the angle is with the horizontal. So if you prefer, get that 28-degree angle for the cable. you know, or not, just depends on how you're comfortable working with things, okay? So remember, you're gonna break up that triangular load. You're gonna have two parts to it, a top and a bottom. The bottom is 800, and then you'll have to figure out the top. Okay, so this height here is 800. That comes from this number right there. So you're gonna have an extra height for the triangle. You're also gonna need to find these dimensions to these loads, which are based on the centroid of the figure. So this one is L over 2, and this other one here, this other distance is going to be what, 2L over 3, because we're coming from the vertex. So this thing has a fair amount of stuff going on with it. You just need to get a nice diagram. That isn't the cleanest diagram, I guess, but that has the stuff on it. That's a little bit muddy, so maybe a little cleaner copy of that would be nice. But anyway, you get the idea there, okay? So now once you've got that, then you just start throwing the equations at it. So any questions on that? So the equations are going to be sum of fx and fy equals 0. If you do sum of fx equals 0, what are you going to have there? You're going to have rax. That's positive because I assumed it to the right. And then minus cosine 28 times 3,000 newtons. So given that, you can solve for rax. Okay. Now, when I do that, I assumed it to the right, so I put it in as a positive. When I solve for it, I'll get a positive answer, and I got 2,649 newtons is what I got. So that is indeed to the right. Okay. You'll also do sum of fy and set that equal to 0. And you'll solve for ray. I think you do have the answers to this, so okay. And then the last thing you do would be to sum moments. When you're doing these cantilever problems, you don't need to really have any sort of fancy strategy for solving them out. Like I say, you just do sum of fx, sum of fy, and a moment usually about the support. Okay. So what I would have there, if I do sum of moments about A, is I'll have m RA, which is the reactive moment at A. That's what I want to solve for. And then I've got minus 2,400 newtons times its moment arm, which is half of 3, so that's 1.5 meters. All right, and then we've got a couple more terms there. So we're going to have another one that's negative, and then we're going to have yet another one too that's negative. Okay, and then you can solve for the reactive moment at A using that. Okay. And you do have the answers to that given it. Let's just be sure, but I'm pretty darn sure you do. Yeah. Great. All right. So we're doing all right with that? Any questions on that? Okay. All right. So that's run through the test there and then this homework that's due tomorrow, okay? Call it good.